In this video, we look at problem number 21 from section 15.4. This is a typical polar coordinates integral. Okay, and we can see that the problem here in number 21 is to do a double integral from y is equal to x up to y is equal to the square root of 2 minus x squared. And they ask us to integrate from x is equal to 0 up to x is equal to 1. And the function you're being asked to compute the integral is x plus 2y dy dx. And we're asked to convert this problem to polar coordinates, which means that we need to turn this into an integral of, if this is a function f of x comma y, then we need to integrate a function of r and theta, r dr d theta, because dy dx turns into r dr d theta. For the area element, here's dA in Cartesian, here's dA in polar coordinates. You need r as a conversion factor. R is in like units of meters, theta is in angular measurement. R d theta together make something and have units meters, so meter times meter is meter squared. So this term r here is a conversion factor to fix the units in the problem. Okay, and then we would need to convert r, fill in the r limits and the theta limits. You can have numbers here on the outer limit, and possibly you could have some function of theta and some function of theta here. So that's our goal, to fill in the blanks. Okay, taking this in steps, I like to look at the function that I'm integrating. If our function is x plus 2y, then because of our polar coordinates transformation, x is equal to r cosine theta, y is equal to r sine theta. That's the transformation. This means that when you put in the function, wherever you see the x, put r cosine theta, and wherever you see the y, put in r sine theta. That means that your function that we are going to be integrating is this function here. Here's your function of r and theta. Okay, so that will get plugged into this spot. The r is taken care of. We've got our fudge factor, our conversion factor. And then the hard part, as it always is with multiple integral problems, is that we need to sketch the region so we can figure out our limits of integration. That's always the hard part, dr d theta. So I multiplied the r through, so now I've got r squared. Okay. And now we need to fill in r is equal to something to r is equal to somewhere else, theta is equal to something, up to theta is equal to something. Okay, and then to do this, we need to be careful. To figure this out, we need to be very careful about the region of integration. Okay, in that region of integration, we're going to try to draw it in the xy plane, right? Because it's the region of the original problem that you were asked to do. So you need to look at these limits and sketch your region of integration. But we were being asked to integrate from y is equal to x. So I'm going to read the bottom limit up to y is equal to x. Okay, so we're going to go from there, y is equal to x, up to, from there up to the next function, which is given by the top function here, which is the equation of a circle. Okay, and this is the circle x squared plus y squared is equal to 2, which means that the radius of this circle is the square root of 2. Okay, so what we can see here is that here's our region of integration. We're supposed to integrate from the bottom function to the top function in y, and x goes from 0 over to x is equal to 1. So So when x is equal to 1, right, we need to figure out where that is. Okay? Is it somewhere here, in which case we're going to have a weird integral to do, or where is x is equal to 1 on this picture more appropriately? Okay? Now remember, square root of 2 is a number bigger than 1, right? And this is a circle. Right here, if I round this out and make it look more circular, this is a circle of radius square root of 2. Okay, so notice here that 1 is less than the square root of 2. Okay, so we're integrating from somewhere around here, and then we are integrating to x is equal to 0 to x is equal to 1. So the region we're looking at is this region here. That's our region of integration. How does that help us with our limits of integration? Okay, so let's take a look here. R is our first limit. The radius, okay, of this edge of the region, how far is that in terms of radius? Right? We'll notice that if x is equal to 1, then y also had to be equal to 1. Right? So what we have there is a triangle where one side of it is 1 and the other side is 1, which makes the hypotenuse square root of 2. So from there to there is a radius of the square root of 2. Okay? So we need to have a radius going from the square root of, 0, because we're imagining circles here, expanding in radius. Okay? And here on this edge, the radius is the square root of 2. If you move here to this part of the region, the radius is square root of 2. No matter where you are inside of that region, the radius will always be a number between 0 and square root of 2. Okay, square root of 2 is the biggest that the radius can be. So our radius will go from 0 to the square root of 2. And the angle, right, we need to figure out what this angle is. Right, at what angle did we get the square root of 2 as our radius? You'll notice that here this says that y is equal to x. Since x and y are given in polar coordinates, x is given by r cosine theta and y is given by r sine theta. This tells you that dividing by r, dividing by cosine. So when is the tangent equal to 1? Which tells you that theta has to equal pi over 4. Okay, so here what we're seeing, we're trying to set ourselves up for, we're seeing that the radius doesn't depend on theta. It's constant. It's the same radius, okay, at its maximum, and the radius builds out from 0 to square root of 2. But the angle part of this region goes from pi over 4 up to, when x is equal to 0, that is going to imply that the cosine is going to be, and the angle will be pi over 2. Okay, so we're going to go from an angle of pi over 4 up to pi over 2, and these angle measurements describe and radius measurements describe the region in question there. Okay, so now we have to figure out what to do with this integral. Okay, you could tackle the inside integral first. I'm sorry, theta goes from pi over 4 up to pi over 2. I meant to write pi over 2 there. Pi over 4 up to pi over 2. And the radius, since you factor out the r squared, you leave behind a cosine of theta plus 2 sine of theta. And then we integrate with respect to r, and you get r cubed over 3. And that r will be evaluated from 0 to the square root of 2, and you'll have a d theta integral left. Square root of 2 cubed That's the square root of 2 cubed over 3. Okay, so we get the square root of 2 cubed over 3, and then we have to do the integral from pi over 4 up to pi over 2. Okay, of cosine of theta plus 2 sine of theta d theta. And there are no difficulties with this integral. This is an easy integral to compute. Okay. If you compute those two, we can check and see if we've converted our integral correctly. Okay, a couple things to check here. Let me move this to the side just a little bit. If we're checking our integral, right, you can put the integral that had the x's and y's in it, which we were asked to convert, x plus 2 times y. Integrate dy dx. X goes from 0 up to 1, and y went from x up to the square root, which was the circle, 2 minus x squared. Okay. That's your integral in terms of x's and y's. Okay. You could have also done what we did in the problem. The problem asked us to convert to polar coordinates, in which case we will get r squared times cosine of theta plus 2 times the sine of theta. Okay. And we will do dr d theta. R went from smallest radius would have been 0 out to r is equal to the square root of 2. The radius stays constant for every value of theta. Theta goes from pi over 4 up to pi over 2. You can check that these will give the same answer. So the answer you're looking to compute with this integral is 2/3 times the quantity 1 plus the square root of 2. And they give the same answer, which is a good sign that we've converted the integral correctly. Another thing you can do is you can check that you've got the correct region. Here we sketched our region. It's this little pie piece right here, so we can probably check that we got the right limits of our integral. We wanted y to be bigger than x, and we wanted y to be less than the square root of 2 minus x squared. And we wanted x to be bigger than 0, and we wanted x, to be less than 1. Okay, and we want to, let's plot that from say 0 to 2, and y going from 0 to 2, just to get a region. And there you can see that that's the region that we had drawn, and for every value of theta, no matter how you rotate, the radius of this region is going to be some number of a radius of a circle between 0, so here are the small circles, and the large circle out here for every value of theta is the square root of 2. So there's your region. Okay. And the reason you would probably find it advantageous to switch to polar coordinates in this problem is because when you're looking at this region here, this part of the circle, or this little pie piece here, okay, that, and here's our y-axis, here's the x-axis. The reason we find this advantageous is because, well, I'm not sure why, for dy dx, it seems like a pretty straightforward integral to set up, going from y equals 0 to y equals up to the circle. So there's just only one integral to compute in dy dx. But if you set this up as a dx dy problem, you would have to compute this problem as two different limits, two different integrals, right? And so Right? If you set this up as a dx integral, you would go from x going from 0 up to x is equal to y, and y would go from 0 up to y is equal to 1. There's your first place where they intersect. Okay? And then you would have x plus 2y. And then if you did the second integral for dx dy, to get the rest of the region here, you would go from x is equal to 0 up to x is equal to the square root of 2 minus y squared, x plus 2y, and y would go from, say, 1 up to y is equal to the square root of 2 at that point. So this is maybe one reason why you would want to do the problem in polar coordinates instead of Cartesian coordinates, x and y, is because in one formulation, dx dy, it's going to take two integrals, right? But, you know, the dy dx doesn't seem like maybe it would be that much of a problem to do, right? So what I'm going to try to finish this problem and ask what would happen if I actually tried to compute that problem as it was originally stated. Would there have been any reason to need to be really required to switch to polar coordinates? Or was this just a problem that you were asked to do for practice? Because sometimes it's necessary that you switch to polar coordinates before you can evaluate the integral. And x goes from 0 up to x is equal to 1. So I don't see anything wrong with doing this dy integral first. You'll get xy plus 2y squared over 2, and then we're going to go from y is equal to x up to y equals square root of 2 minus x squared, which means that you'll get x square root of 2 minus x squared plus the square root of 2 minus x squared. There's your top limit. And then when you subtract the bottom limit, y is equal to x, you get minus x squared plus x squared. Okay, so there's your minus x squared, minus, put in the x into y, you get x squared plus x squared. So you get the integral from x is equal to 0 to x is equal to 1, x square root of 2 minus x squared plus 2 minus x squared minus 2x squared. Right. Paying careful attention to the minus signs. Okay, so still not seeing anything that's going to be really difficult in our future, x going from 0 to x is equal to 1, x square root of 2 minus x squared dx plus the integral from x going from 0 to 1 of 2 minus 3x squared dx. Okay. So this integral, easy. And this integral is a u substitution integral, okay, with u is equal to 2 minus x squared. Du would be negative 2x dx. So this integral will get converted to negative 1/2 square root of u du. And when x is equal to 0 here, u will be equal to 2, and when x is equal to 1, u will be equal to 1. And again, this is an easy integral to compute. Okay, and those integrals, when you compute them, okay, will give you 2/3 1 plus square root of 2. So I'm going to say that this problem that we've been given and posed in question number 5.421 is one of those problems that is converted to polar coordinates because they want us to practice converting to polar coordinates, not because it's really necessary. Okay? So I hope that this video helps and you getting the answer to this problem.